We will now talk about conditional probability. So in this case, assume we have a probability measure, which means we are given a sample space, a sigma algebra F, and a probability measure P. Then suppose there are two events A and B. Events, when I say events, both need to be in F, sigma algebras, and they are both subsets of omega. This will ensure the probability is defined on these events. And we have an additional condition that probability of B should not be 0. Right? This means the B should occur with some non-zero probability. Then the conditional probability of A given B has occurred is defined as probability of A given B has occurred is equal to probability of A intersection B divided by probability of B. So how do we understand this? This basically refers to the probability that if we know that B has occurred, then what is the chance that A has also occurred? So we can understand this also from the Venn diagram. Let's assume this rectangle denotes the complete sample space. Then there are two events A and B where there is some intersection. There is some overlap between these two sets. So remember, this picture depicts so that every point of this capital omega is an outcome. Okay, so omega is a set of outcome. So every point in this is a outcome. And then when I say this A, it contains the point where of outcomes where A has occurred. So A is also a set of some outcomes, and B is also set of some outcomes. Okay, and the intersection part between A and B denotes the event which are also in A and also in B, which means if this set has occurred, which is A intersection B, so A intersection B is also an event. If A intersection B occurs, which means A also occurs and B also occurs. This means A intersection B occurs means there is such an outcome has occurred, which is also in A and also in B. So which means A has also occurred and B has also occurred. So what I do is I take this B, compute the probability of B, and then I take this A intersection B and compute the probability of that. And then the ratio of the two is known as the probability A given B, which denotes that if I look at only on the outcomes where B has occurred, what is the probability, relative probability that A has also occurred. So that is how we get P A intersection B divided by probability of B. It is the ratio of this probability of this set and probability of the complete B. Similarly, probability of B given A would be given as probability of A intersection B divided by probability of A. So even to go further, we have to first prove that this probability is also a probability measure, right? We have to prove that the new probability measure probability A given B is also a valid probability measure. So let's denote it this way. Let us assume P1 is defined as probability of given B, right? So this means you can put any set here, A here in sigma algebra. So probability of A would be equal to probability of A given B. Probability of C would be probability of C given B. So this is a new probability measure which we call P1. And P1 of C is probability of C given B. This is the original probability measure we have considered. And this will be equal to, by definition, this will be equal to probability of, if this is C, this will be probability of C intersection B divided by probability of B, which is the probability that C also occurs when we know B has occurred. Okay, so this notation is partly known as is defined to be. So this is where we are not saying they're equal, we are saying they're defined in this way. So of course they would be equal. So how do I prove that this measure is a valid probability measure? For that, I have to satisfy the three properties. One property is that the probability of omega should be 1. So let us see. So if I put P1 of omega, which is equal to P of omega given B, then by definition this will be equal to probability of omega intersection B divided by probability of B. And B is always in omega because omega is the complete sample space. So omega intersection B is nothing but just B. So this will be probability of B divided by probability of B, and that should be equal to 1 because we have assumed probability of B is not 0. Then I have to prove probability of phi is 0. So P1 of phi is equal to probability of phi given B, which is equal to probability of phi intersection B divided by probability of B. And again, phi intersection B is nothing but just phi. And P phi is 0 because P is a probability measure. So if P is a probability measure, P1 would also be satisfy this property. And the third property we have to satisfy is that countable additivity, which means P1 of union of AI should be equal to summation of P1 of AIs. And if I apply the definition of P1, this is the equivalent of saying that for disjoint sets, probability of union of AI given B should be equal to summation of probability of AI given B. Right. So how do I prove this? And we are already given that P is a valid probability measure. That is known. We have to just prove that this conditional probability is also a valid probability measure. So if we look at the left hand side, probability of union of AI given B is equal to probability of a union of AI given AI intersection B divided by probability of B. So you can look at this as complete C. So probability of C given B is probability of C intersection B divided by probability of B. Okay. Now we have to compute this intersection with the union, right? And we know that union is distributive. So this is equivalent of saying that it's the union of AI all into AI intersection B. Okay, so if you take two sets A1 and A2 and want to compute the intersection of B with A1 union A2, this will be equivalent if you take the individual intersection with A1 and A2 and then take the union. This can be very easily proven using a Venn diagram. So from this, now this is just probability. There is no conditional. So I can apply the countable additivity property in the numerator, and from that I get this is equal to summation of probability of AI intersection B, because you treat this as a set C. So this is probability of intersection, probability of union of C is equal to summation of probability of C. So this is how you get this, and there is a probability of B. Now you can take this summation out of the ratio, which will get probability of summation over n, probability of A intersection B given divided by probability of B, which is by definition equal to probability of A given B. Okay, so we have proved that countable additivity property is also satisfied by P1. So since P1 satisfy all three properties, P1 is a valid probability measure. So it will satisfy all other properties of probability measure also. So let us see an example of conditional probability. Let us consider an example of two coin tosses. So omega is made from four outcomes: HH, ST, TH, and TT. Let A be the event that the first toss is had, and let B is the event that the second toss is had. So what is A in terms? What is the exact definition of A? A would be equal to HH comma ST because it is made from two outcomes. Similarly, B is would be equal to HH and TH, which denotes the all the outcomes where second toss is had. So what is the probability that given B, A has occurred? It means given that the second toss is had, what is the probability that first toss is also had? Okay, so you can intuitively think when the second toss is had, this will represent B, and the probability of there are two events in this, and there are two outcomes in this, and all of the outcomes are equally likely. So there are two outcomes which support that the second head is second coin toss is a head. And now I am interested in knowing that given that this, A also occurs, which means the first coin also gives you a head. So this means the second coin is a head and the first coin is head, which is only one outcome HH. So out of two outcome, I am interested in knowing what is the chance of this one outcome occurs. So probability would be 1 by 2 because they are all equally likely. So this can also be shown uh, in this way. We can say probability of A given B is equal to probability of A intersection B divided by probability of B, and A intersection B is nothing but just HH, and B is HH comma TH. So this will be equal to probability of HS divided by probability of HH comma TH. If they are they are fair coins and every event is equally likely, then this will be equal to 1 by 2. If they are not, then of course this will be different. Then from conditional probability, we get one more equation. If you look at the definition, it is equal to probability A given B is equal to probability A intersection B divided by probability of B, which will give us the another expression saying that probability of A intersection B is equal to probability of B into probability of A given B. Okay, so if you want to compute the probability of A intersection B, you can take one event, prob B, and compute its probability of B, and then you can condition on this B and compute the probability of A. And then if you multiply that, you will get the probability of A intersection B. Okay, so remember this, probability of A intersection B is not always equal to probability of A into probability of B, but it is equal to probability of A given B into probability of B. So this formula is known as the chain rule. Right. Now there is another interesting law which is known as total probability law. Right. So how we can understand this? Suppose there is a omega and there is an event A, and I'm interested in knowing the probability of A. But somehow I cannot directly compute this A. So what I did is I divided the space into two convenient partitions, B1 and B2. So partition means this B1 and B2 are disjoint, and B1 union B2 should make the complete omega. So that is the definition of partition. So now I am saying is uh, A is nothing but the union of A intersection B1 and A intersection B2. Right? Is that clear? A is made from these two parts. This part is A intersection B1 and this part is A intersection B2. So A is is written as A intersection B1 union A intersection B2. Now, because these are disjoint sets, so probability of A would be equal to probability of A intersection B1 plus probability of A intersection B2. Right. Now, what is probability of A intersection B1? It is given by probability of B1 into probability of A given B1. This is chain rule. Similarly, here also probability of A intersection B2 is probability of B2 into probability of A given B2. This is known as total probability law, and you can do even more partition, just like n partitions. And then it just means that if you are interested in knowing the probability of A, you can take two events which are disjoint and mutually which are complement to each other. Then you can compute the probability of A given B1 if that is convenient, and probability of A given B2. And then if you multiply them individually with probability of B1 occurring to the probability of A given B1, and then probability of B2 occurring into probability of A given B2, then if you add them, you get the total probability. Okay, so this is very intuitive to understand. A given B is probability of A given B has occurred, right? And if you multiply it with the probability of B also, you get the overall probability of A and B both occurring. Okay, so this is the probability of A and B1 both occurring. This is the probability of A and B2 both occurring. If you add them, you will get just the probability of A, right? Because one of the B1 or B2 will always occur. So union of these two will be just probability of A. This is known as total probability law, and we will be using it multiple times. Total probability law can also be extended for a general partition. Suppose there is a partition, n partition, where you are dividing omega into b1, b2 up to bn. Then the probability of A would be given by probability of bi into probability of A given bi, and then you sum it over all partition. So this denotes the probability of A intersection bi. So you have divided A into many parts by this partition, and this will be A intersection b1, A intersection b2, A intersection b3, A intersection b4. And if you add all those probabilities, you get a total probability of it. And the individual probabilities B given intersection, sorry, A intersection B1 is nothing but probability of B1 into probability of A given B1. Right. Now we will talk about independence. So we say two events A and B in any probability space are independent if probability of A intersection B is equal to probability of A into probability of B. So this is not always true, but whenever this is true, then only we will say that A and B are independent. So this is the definition of independence. So if you are ever asked to know whether to calculate where two events are independent or not, you will just check whether the probability of their intersection event is equal to probability of product of their individual probabilities. So if the events are independent, then what will be the conditional probability A given B? Okay, let us understand this. So conditional probability of A given B is equal to probability of A intersection B divided by probability of B. Now by independence of A and B, the probability of A intersection B should be equal to probability of A into probability of B. So if you divide by probability of B, you just get probability of A. So this means in the case of where A and B are independent, probability of A condition B is equal to probability of A. Means conditioning with B does not change the probability of A. So that is why they are called independent, because when you condition that B has occurred, then you ask what is the probability of A is occurring. It is the same as if you have not conditioned. Okay, so that is why this independence we are saying. So both are valid formulas. Either you can prove if this formula that A intersection B probability is probability of A into probability of B, or if you prove that probability of A condition B is equal to probability of A. In both cases, they are same condition, and we will call that probability. We will say that A and B are independent. Okay, and this basically affect that the occurrence of B does not affect the chances of occurrence of A. So we will see one example. So let us assume that you are doing two coin tosses together, and the outcomes are HH, TH, ST, and TT, and the probabilities are 1 by 4, 1 by 4, 1 by 4, 1 by 4. It means each of the singleton event has equal probability. Now, if we have consider an event where coin 1 shows heads, which is equal to A, HT, HH, and B is the event where coin 2 shows head, which is TH and HH, then the probability of A would be equal to half. The probability then, and probability of A condition B, which is probability of A intersection B divided by probability of B, is also half. So in that case, conditioning with B does not change the probability of A. So we will say probability of A is independent of probability of B, which here also implies that the chances that the first coin shows a head is independent of whether the coin 2 shows a head or tail. Okay, but you can verify that this is not always true if you have a different assignment. If these four outcomes are not equally probable, then you will see that if you condition on B, the second coin toss may change the outcome of the first coin toss, and then they would not be independent.